All right, this presentation was prepared by Dr. Nima Madian. Now let me ask you something. Have you ever tried to understand a system when its true nature is completely hidden? I want you to picture a black box. You know what goes in, and you can measure what comes out, but that output signal is all messy and garbled, totally corrupted by random noise. So how in the world can we figure out what's actually happening inside that box? Well, that's the exact mystery we're going to solve today.
Okay, so here's the core problem we're up against. We've got what's called a linear time invariant system, an LTI system. For our purposes, you can just think of it as this black box which we'll call G0. We send in a signal that we know, our input, U of t, and then we measure what comes out, Y of t. But, and this is the big but, the main villain of our story is that our measurement is being corrupted by some unknown disturbance, a noise we'll call V of t. Our entire mission here is to find a really accurate estimate of the system's true response, even with this noise trying its best to throw us off the scent.
So where do we even begin this investigation? Well, the most obvious place to start is with the simplest approach, right? In system theory, a transfer function is basically just the ratio of the output to the input. So let's try doing that in the frequency domain. By taking something called the Fourier transform, we can break our signals down into all of their different frequency ingredients. The idea is simple. Just divide the output's frequency ingredients by the inputs. This is called the empirical transfer function estimate, or ETFE for short. It's direct, it's intuitive, but the real question is, does it work? And here's the big twist. Just take a look at this graph. The smooth blue line, that's the real system we're desperately trying to find. And that jagged, chaotic yellow line all over the place? Yeah, that's our ETFE estimate. It's a total disaster. And here's the fatal flaw. Its variance, or its jumpiness, doesn't get any better as we collect more data. You could run this experiment for an eternity, and the estimate would stay just as noisy. We're not actually seeing the system, we're just seeing the noise. Our first and most obvious approach has led us absolutely nowhere. It's a complete dead end.
So this brings us to a really critical point. If the most direct, the most obvious method is a total failure, if it's completely swamped by noise, how can we ever hope to see the true system that's hiding underneath it all? It really starts to feel like an impossible task.
But this is the aha moment. This is the key insight that unlocks the entire puzzle. You see, the ETFE failed because it was looking at every single frequency point all by itself. But real physical systems just don't work that way. Their frequency response is typically a smooth function. The value at one frequency is very closely related to the values at the frequencies right next to it. And we can use this to our advantage. By averaging the noisy values in a small window of frequencies, the random ups and downs from the noise will actually start to cancel each other out, revealing the beautiful, smooth trend of the true system underneath.
Okay, so how do we turn that brilliant insight into a method we can actually use? We make it official using a mathematical tool called a window function. You can think of it like a moving spotlight that we shine on a small range of frequencies. It performs a weighted average, so it gives more importance to the frequencies right in the middle of the spotlight. This leads us to what's called the Spectral Analysis estimator. And as you can see, it's no longer just a simple ratio, it's a ratio of the smooth spectrums. We've literally built our key insight right into the mathematics.
Now, this new method is incredibly powerful, but it comes with the classic engineering problem, the bias-variance trade-off. Think of it like a seesaw. On one side, by averaging or smoothing, we get rid of that random spikiness from the noise. That's a reduction in what we call variance. But it comes at a price, and that price is bias. By smoothing everything out, we risk blurring over sharp, really important features of the real system. The width of our averaging window becomes the knob we turn to trade one for the other.
Let's break this down. First, what's the real cost of all this smoothing? Well, it's bias. This happens when our averaging window is just too wide, and it ends up smoothing over important, sharp details in the system's actual response. So if the real system has, say, a very sharp peak or a sudden valley, our smoothed estimate might just skim right over it, blurring that detail out. So a wider frequency window means more potential for blurring, which means more bias.
But now for the benefit. Why does smoothing work so darn well against noise? Well, a wider frequency window means we're averaging more of those random noisy data points. And the more points we include in our average, the more the random ups and downs just cancel each other out. The key takeaway, which you can see captured in this formula right here, is that the variance drops as we widen our window and include more data. And this is what gives us that much cleaner, more stable, less spiky estimate.
So this turns our abstract trade-off into a super practical guide for any engineer.
It's basically the decision matrix. If you absolutely need to see the sharp peaks, the resonances, all the fine details in your system, you have to choose a narrow window. You'll have to accept a little more random noise to get those details right. But if you just need a stable, low-noise overview and the tiny details aren't as critical, then you go with a wide window, accepting that blurriness in exchange for that clean, low-variance result.
So, check this out. We've developed this incredible tool for finding the system, RG0. But this brings up a really fascinating new question. Can we turn this powerful tool back on the original problem, that ghost in the machine, and actually identify the characteristics of the noise itself? Because, in a lot of real-world applications, understanding the noise is just as important as understanding the system.
And the answer is a resounding yes. And the method is just wonderfully elegant. It's a simple three-step process. First, you get the best possible estimate of your system using the method we just discussed. Second, you calculate what are called the residuals. That's basically the signal that's left over. It's the part of the output that your system model can't explain. This residual is our best guess at what the noise actually is. And third, you just treat that residual signal as its own time series and apply the exact same spectral analysis method to it. Boom, you get a clean estimate of the noise spectrum. But with all this estimating going on, how can we really be confident in our results? We need a quality check. And that's exactly where the coherence function comes in. Think of it as a built-in lie detector for your estimate. At any given frequency, if the coherence value is close to 1, that tells you the output is highly connected to the input, noise is low, and your system estimate is solid. But if that value is near 0, that's a big warning sign. It's telling you that frequency is dominated by noise, and your estimate there is pretty much pure guesswork.
So let's just take a quick step back and look at the awesome journey we've been on. We started with a huge problem, a simple estimate that was totally useless because of noise. Then we discovered a key insight: real physical systems are smooth. This led us to develop a formal method, spectral analysis using a window. This method forced us to navigate a fundamental trade-off between bias and variance. And finally, we extended this powerful technique to a whole new application, estimating the noise itself.
And this slide just brilliantly illustrates the final payoff. I mean, just look at the difference. On the left, you've got that raw, noisy mess we started with, the ETFE, which tells us basically nothing. And on the right, you have the result of applying our refined insight, a clear, clean, and understandable model of the system we were looking for. By embracing that core principle of smoothness and intelligently managing that bias-variance trade-off, we have literally transformed useless noise into powerful insight.
And that leaves us with one last provocative thought. We've just walked through a seriously powerful technique for pulling a clean, hidden signal out from a noisy background. So the question to leave you with is this: what other hidden systems, what other important signals are just waiting to be uncovered in the massive amounts of data that surrounds you every single day?